Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, this is lecture 9 of the course of CS352 Introduction to Soft Computing, and we'll be basically talking about control systems and AI, specifically the application of fuzzy logic in control systems. This lecture is specifically about section 9.2, and in the previous section 9.1, I have basically introduced the main concepts of fuzzy logic to you. We have taken examples and seen that in specific cases in control systems there are specific issues which cannot be simply resolved by the traditional AI based methods and by the traditional crisp sets. So in this lecture I'm going to go more into the theory of fuzzy logic and fuzzy systems, and specifically I'll talk about what is the real issue with the crisp systems due to which they cannot be applied to control systems, and then we'll develop the basic mathematical background that is necessary to understand fuzzy logic. I'll talk about fuzzy sets and crisp sets, and I'll try to differentiate between them so that you are absolutely clear about why we are studying fuzzy logic. In the next lecture I'll build on this knowledge and probably give you concrete rules and membership functions and concrete algorithm as well to deal with fuzziness in the system. And of course then after that lecture we are finally going to talk about the applications in a specific application, and in that I'll basically be talking about a room cooler and how we have used different rules to infer the speed of the fan. But for now, let our focus be completely on fuzzy sets and basically crisp sets, and try to compare them, and let's at the end come up with a fuzzy system, and let's see the mathematical properties of fuzzy system. So let's start with the agenda for this lecture of section 9.2 fuzzy sets. I'll first be introducing to you what fuzzy sets are, basically by kind of comparing them with crisp sets. Then we'll see a specific example of a fuzzy set where I'll take age and I'll describe the fuzziness in the system. Then I'll talk about the salient features of a fuzzy logic system by basically again comparing it with the features of a crisp set, and then talking about the differences with the fuzzy set. Then we'll talk about the mathematical concept and the representation of a fuzzy set, which will then be followed by the different operations that are present in the crisp sets as well as in the fuzzy sets, and this will also be followed by the various properties, for example associative law and the other different mathematical laws that are present in crisp sets, and then show you how they can be applied or if they can be applied to fuzzy sets. It will then be followed by the definition of a membership function and what it constitutes, what it looks like. And since we are talking about fuzzy logic and fuzzy sets, of course the value of a qualifier, as you already know from your discrete mathematics, would become handy, and I'll show you what fuzzy qualifiers are. It will then be followed by the description of a fuzzy system and how we can convert the mathematical background and logic that we've looked at in this section to come up with a fuzzy system. And finally, of course, then we have a summary and key points followed by a list of reading for you. So let us formally start the lecture on section 9.2 with a description of the differences between crisp sets and fuzzy sets. And to do that, we first need to identify what are crisp sets. So in a crisp set, members belong to the group identified by the set or they do not belong to the group. So there's only two options. It's either you belong to the group or you do not belong to the group. For example, in case you want to define slow and fast, S is a member of the group slow or set slow such that the value of S is between 0 and 40, while fast will then be defined as every member S such that the value of S is between 40 and 70. So let's say a value of 40.1 is belonging to the set fast and it is not belonging to the set slow. It can be basically be belonging to certain sets only, and it either belongs to them or it does not belong to them. So what are the drawbacks of crisp sets that we have been using and that we have been seeing throughout our education so far? Suppose a physical system has to apply brakes if the speed of vehicle is fast and release the brake if the speed is slow. So if the speed is in the interval 39 and 41, then such a system would continuously keep jerking, which is not desired. So that is the drawback of using crisp sets. Okay, so here is where the fuzzy sets would come in. To reduce the complexity of comprehension, vagueness is introduced in crisp sets, and that's the basic idea of fuzzy sets. Fuzzy set contains elements. Each element signifies a degree or grade of membership to a fuzzy aspect. Membership values denote the sense of belonging of a member of a crisp set to a fuzzy set, and that's it. So in fuzzy sets, one object can belong to multiple sets with varying degrees. You can both be slow and fast at the same time, but with a different degree, and that will result in possibly a different degree of output as well. So that particular membership value denotes the sense of belonging, and that's the highlight of a fuzzy set. So let us see an example of a fuzzy set to clarify the concepts that I gave in the last slide and to differentiate it with the crisp set. So let us start with the crisp set A, with elements representing ages of a set of people in years. And here A is, for example, 2, 4, 10, 15, 20, 30, 35, 40, 45, 60 and 70 years. We want to classify the age in terms of 6 fuzzy variables or names given to fuzzy sets as, for example, infant, child, adolescent, adult, young and old. So the membership is different from probabilities. You need to understand this point very well. Memberships do not necessarily add up to 1, while probabilities will always add up to 1. So that's the first and foremost major difference. So what we can see here, for example, if you see on the right side, you can see that you have got these ages. That's 2, 4, 10, 15, 21, 30, 0, 40 and so on. These are the ages of different people, and we can basically put them in 6 fuzzy variables: infant, child, adolescent, young, adult and old. And for example, if someone is 2 years old, then he's basically he has full membership of infant and he has full membership of young as well. If you think of it as probability, you'll probably observe that the probability should add up to 1 if you belong to 2 groups, and you do it up in a probabilistic manner, then it should sum up to 1. That's not the case at all in this case, and this sum would be different. So that's where a fuzzy set differs from a probabilistic set directly. So let's say it like that. And then you have got, for example, 4. We can put in a membership value of that he's 1 to young, and 0.5 to child, and 0.1 to infant, and so on for all the different ages. So keeping this table in mind, let's try to categorize a person with age 30 years. Or let's try to answer the question that if a person is 30 years old, how would we characterize it or categorize it? Similarly, a person with age 40, is he old? If we look at table 1, it shows the fuzzy sets, namely ages: infant, child, adolescent, adult, young and old.
The values in the table indicate the membership to the fuzzy sets. For example, consider the fuzzy set child, and what we observe is a child with age 4 belongs to the fuzzy set child with 0.5 membership value, and a child with age 10 is 100% member of this group. So that's the way you are going to read it. So answering the first questions, as per the table 1, a person with age 30 is 60% young and 100% adult. A person with age 40 is 40% young and 100% adult. A person with age 60, if you look at the right column, is 100% adult and 80% old. So that's how you're going to read these tables and examples. So this brings us to the features of fuzzy sets. After having seen both examples of a crisp set and a fuzzy set, what are the salient features of fuzzy sets? A complex nonlinear input-output relation is present as a combination of simple input-output relations. The simple input-output relations is described in each rule. The system output from one rule area to the next rule area gradually changes. Fuzzy logic systems are augmented with techniques that facilitate learning and adaptation to the environment. Thus, logic and fuzziness are separate in fuzzy systems. In conventional two-value logic based systems, logic and fuzziness are not different. Fuzzy logic systems modify rules when logic is to be changed and change membership functions when fuzziness is to be changed. So with these things in mind and with these major differences between conventional two-value logic systems and the fuzzy logic systems, you can kind of get a basic inference or basic guidelines to when a fuzzy set is useful and when a conventional logic set is useful. And we'll start off with the classical set theory and then start with the fuzzy set theory. So what is a classical set? A set in a classical set theory is an unordered collection of different elements. You can mathematically represent a set in either tabular form or in roster form or as set builder notation. The cardinality of a set is defined as the number of members that are contained in the set. And then there are various types of sets that we are already aware of through our discrete maths and other mathematics classes. We have got a finite set, infinite set, subset, proper subset, universal set, empty or null set, singleton or unit sets, equal sets, equivalent set, overlapping set, and disjoint set, etc., etc. So there are a lot of these types of sets that we observed. Then you have got several operations that are defined for classical sets. For example, we can perform a union, intersection, difference or relative complement, complement with the universal set, Cartesian or cross products, etc., etc. Also, a lot of properties have been done and have been decided for classical sets. For example, we know of the commutative property, we know distributive property, associative property, idempotency property, identity property, transitive property, involution, and De Morgan's law. So that's how a classical set behaves. Now we'll try to look at how these all things fit in for fuzzy sets. Fuzzy sets can be considered as an extension and gross oversimplification of classical sets. It can be best understood in the context of set membership. Basically, it allows partial membership, which means that it contains elements that have varying degrees of membership in the set. From this, we can understand the difference between classical set and fuzzy set. Classical set contains elements that satisfy precise properties of membership, while fuzzy set contains elements that satisfy imprecise properties of membership. What you can see here as an example is there's a basically fuzzy set A, and if you look at the membership function of that fuzzy set, it's kind of peaking at a certain point, but has also a varying degree of membership of a value between 0 and 1 for other places. While if you look at the classical set, it's basically a step function. You're either 0, you don't belong to the category, or you completely belong to the category, you are completely in the set, and then you again not in the set. So where there is a partial degree of membership, where there is basically a curved function, This particular case is where the membership function of a fuzzy set is being defined. But if you look at the step function, in this special step function where the values are either 1 or 0, you either belong to the set or you don't belong to the set. That's the classical set theory. So let us talk about the mathematical concept of fuzzy sets. A fuzzy set A in the universe of information U can be defined as a set of ordered pairs, and it can be represented mathematically as set A is basically the set of all ordered pairs, where the first element is the member Y and the second element is the membership value of the member Y, and all these Y are basically members of the universal set U. Here the membership function mu represents the membership function and or the degree of membership, and mu ay means set A element Y and the membership function mu represent degree of membership of Y in A. It assumes the values in the range from 0 to 1, that is, it precisely belongs between 0 and 1 inclusive. So let us now talk about representation or information in fuzzy sets. Let us now consider two cases of universe of information and understand how a fuzzy set can be represented. Of course, the first case is when the universe of information is discrete and finite, and the other case is when the universe of information is continuous and infinite. In case of discrete and finite members, it is usually represented by a sum, while in case of continuous and infinite information, it is represented by integration of the function. Here is basically the membership function divided by the value itself, right? And similarly, the membership function divided by value itself, if you take the integral of it, it becomes continuous. If you take sum of it, it becomes discrete. In the above representation, the summation symbol represents the collection of each element. So you need to collect them all, and that is going to define the universe of information. So as we had discussed earlier, on the crisp sets, there were some certain operations that could be performed. Similarly, we can also define operations on fuzzy sets. So for example, if I have two sets A and B and both are fuzzy sets as shown here, you can see the membership functions and then the graphical description. The union of both the fuzzy sets is going to add both of them up and come up with a value that is kind of common between both of them, and the red line here shown on the union function should displays that after taking the union, it's going to combine both of them. On the other hand, if we talk about the intersection, that is going to be the common region between both the sets, and that is again represented by the red line here. And similarly, we can also define, of course, the complement of a fuzzy set. So let us suppose that you have a set U, you have a set A, and you want to find its complement. You have to subtract it from 1, you have to inverse it. So the complement of set A is going to be the you take the line 1 as a whole, and wherever the value of A occurs, you basically subtract it from 1. Wherever A is 0, you basically let it remain at 1. The dotted line here represents the complement value of the set A. You can see that the set A has basically got a triangle, and the complement is basically the inverse triangle, starting at 1 and ending at 1 as well. So just like crisp sets, fuzzy sets also have similar properties and similar laws. So we already know what the commutative property is: associative property, distributive property, idempotency property, identity property, transitive property, involution property, and De Morgan's law. They can be exactly applied in the same manner to fuzzy sets as well. And for that, for example, let's talk about the simple case of finding a union with, let's say, an empty set, or intersection with the universal set. In both cases, you get the set A back, the crisp set A back, and if you intersect with an empty set, you get an empty set back, and if you find union with the universal set, you actually find the universal set back. So you can see that the properties are exactly the same and work in a similar manner as compared to the actually the crisp sets. So you don't need to worry about the properties, you need to remember them, and you might have to actually use them in some questions if you get something. So you need to remember the operations, and you need to then find maybe proof of these properties. You can do that easily on your own. So very important concept in fuzzy logic is the concept of membership functions. Remember, fuzzy logic is not logic that is fuzzy, but instead logic that is used to describe fuzziness. This fuzziness is best characterized by its membership function. So membership function represents the degree of truth in fuzzy logic. Of course, the membership functions were first introduced in 1965 by the Lutfi A. Zadeh in his first research paper of fuzzy sets that I've shown in the prelogue now. Membership functions characterize fuzziness, that is, all the information in fuzzy set, whether the elements in fuzzy sets are discrete or continuous. As we have seen, membership functions can be defined as a technique to solve practical problems by experience rather than by knowledge. Membership functions are represented by graphical forms. Remember, the rules for defining fuzziness are fuzzy too. And here's a typical example of a membership function. So you can see that for values in a certain range, the set is showing that the mu value is 0. Then beyond at a certain time, it starts to increase, and it's a value between 0 and 1. Then there comes a time when it reaches approximately exactly 1, and then it starts to to fall down as well, and basically it goes down to 0, and beyond that point it's 0 onwards. So this represents a typical membership function mu, and the value of mu for the member y in the set A. So that's how you're going to read this up.
So what are the features of membership functions of fuzzy sets? There are three main features of membership functions. The first feature is called the core space or the core feature. Secondly, we have got the support feature, and finally we have got the boundary feature. Each of the features can be defined by the following definitions. For core, for any fuzzy set A, the core of a membership function is that region of universe that is characterized by full membership in the sense. Hence, core consists of all those elements y of the universal set of information such that the membership function of that those elements y is equal to 1. And you can see the core function in the diagram as the one where the membership value is exactly 1. The second region is the support region, where for any fuzzy set A, the support of a membership function is the region of universe that is characterized by a non-zero membership in the set. Hence, core consists of all those elements y of the universe of information such that the membership function of y returns a value greater than 0. And there you can see the support function is basically including the core as well as other regions where the support value is greater than 0. Then if we talk about the boundary of the fuzzy set, for any fuzzy set A, the boundary of a membership function is the region of universe that is characterized by a non-zero but incomplete membership in the set. Hence, core consists of all those elements y of the universe of information such that 1 is greater than the membership function of y is greater than 0. So here what you can see is the boundary function will consist of all the regions, all the support regions that are not core. Or another way of defining support would be core plus boundary regions. So boundary regions are the regions which have a value greater than 0 but strictly less than 1. The core are the regions where the value is strictly equal to 1, and support consists of boundary plus core, that is all those values where the membership function returns a value greater than 0 will be called support.
Fuzzy qualifier is also a proposition of fuzzy logic. The fuzzy qualification has the following forms: the fuzzy qualification based on truth, fuzzy qualification based on probability, and fuzzy qualification based on possibility. In fuzzy qualification based on truth, it claims the degree of truth of a fuzzy proposition. For example, the expression is expressed as x is t. Here, t is a fuzzy truth value. For example, car is black is not very true. So the proposition that car is black is not very true. So the terms not very expresses qualification based on truth. Another way we can define fuzzy qualification is basing it upon probability. The fuzzy qualification based on probability claims the probability, either numerical or an interval, of fuzzy proposition. The expression is expressed as x is lambda, where lambda is a fuzzy probability. For example, car is black is again a statement, and this statement is likely. So you are kind of giving it a particular probability. Then we have got fuzzy qualification based on possibility, which claims the possibility of a fuzzy proposition. So the way it is expressed is x is lambda, here x is pi, and here pi is a fuzzy possibility. So for example, car is black, which is again the same statement, is almost impossible, is highly possible, is possible. If you explain it in these terms, then this is basically fuzzy qualification based on possibility. Fuzzy systems, neural networks, and genetic algorithms are a part of soft computing technologies. Assume that the problems to be solved belong to a multi-dimensional input-output space or search space. For example, a 2-input and 1-output space where the inputs and outputs are related with nonlinear function. The objective is to find the best input that produces the required output. Uncertainty is inherent in accessing information from large amount of data. For example, words like near and slow in sentences like my house is near to the office or he drives slowly. If we set slow as speeds less than equal to 20 and fast otherwise, then is 20.1 fast? Fuzzy systems and neural networks model such complex nonlinearity by combining multiple simple functions. Neural networks use sigmoid or other simple functions and synaptic weights. As you might already know from the course of CS351 Artificial Intelligence, fuzzy systems use several rules and membership functions. Fuzzy logic deals with techniques to capture the essence of comprehension and embed it on the system. Thus, using fuzzy logic, a gradual transition from slow to high speed is allowed. Due to the comprehension, fuzzy logic provides higher intelligence quotient to machines.
Okay, I wanted to end my lecture on by basically showing you what a fuzzy system looks like and what are the various main components that are present in a fuzzy system. Of course, we'll be studying these components in a lot more detail in the next lecture. But just to give you a bit of food for thought for the next lecture, I'll just be talking about the flow chart, if you want to call it, of the fuzzy logic based system. What we have is we usually start off with system inputs, which are shown here in red. Those system inputs are then passed to input fuzzification unit, which fuzzifies them, and it fuzzifies them using membership functions and rule based information. From input fuzzification, we get basically degrees of membership of these fuzzied values. and these degrees of membership are then passed to the rule evaluation, which again uses the rule base and membership function to kind of evaluate the different input based on rules, and then it generates an output which is again a fuzzy value, and it's basically and the membership function which we call here as output strengths as well. So these output strengths and the output values are then passed to the defuzzification unit, which is used for defuzzification. And after defuzzification, of course, we get a crisp value for the output that we really need as a result, and this is the our system output then, which can then again be passed to system input, or if it's different then it can be used separately. So that is the overall working of a fuzzy logic based system. And in a fuzzy system, you're typically going to see a fuzzification unit, an evaluation unit, and a defuzzification unit for the output. And that is the overall mechanism that you will see in air conditioners, in a lot of other examples that we're going to take up in maybe in the next lecture or the lecture after that. So that is it for this lecture, I guess, but we'll of course now move on to the summary and demo. Okay, so let's summarize and let's bring this section to an end. What we have studied in this lecture is basically that the fuzzy sets share as well as differ in a lot of different variety of points from crisp sets. Similar operations and properties can be defined for both the crisp and the fuzzy sets. For example, we have seen the union, intersection, etc. in terms of operations, complement as well, and in terms of properties we have seen those different laws, associative, commutative, and all the other laws that are kind of very much common for both the crisp and fuzzy sets. However, fuzzy sets primarily differ from classical sets or crisp sets in the membership function. And what a membership function is, in a typical crisp set, a reading can belong to exactly one element at most, or maybe zero element of a crisp set. But in a fuzzy set, a single reading may belong to any number of elements in a fuzzy set, of course with a degree of membership of each of these members using a membership function. Membership functions can be divided into core, into the support, and into the boundary regions as we have seen, and we've seen the mathematical derivation of these as well, or the mathematical representation, where core is basically where it is exactly equal to 1, and then you have got support similarly defined, and as well as for the boundary regions as well. The classical set contains elements that satisfy precise properties of memberships. So you either belong to the to a particular set or you don't belong to it. So that's the precise manner. However, fuzzy sets contain elements that satisfy imprecise properties of membership. You can belong partially to an element of a set as well. Then we have seen that fuzzy systems, neural networks, and genetic algorithms are all part of soft computing technologies, and we have studied them in different contexts in this course. Although neural networks was not studied in detail here because you are already studying that in the artificial intelligence CS351 course. Fuzzy qualifiers can be classified into 3 distinct classes, and we have seen them. They can be based on truth, they can be based on possibility, and they can be based on likelihood. And finally, we have basically seen how a fuzzy system looks like and what are the main 3 components: the input fuzzification, the rule evaluation, and the output defuzzification units. That's it for this lecture. I hope you have learned something from this, and I hope the concept of fuzzy sets and crisp sets is absolutely clear to you. If not, please go back and look at the main concepts of fuzzy set theory. With that, I wish you all the best.